Okay, good morning everybody. Welcome everybody to our next session on basics of video technology. So last time we saw what happens when we do downsampling, basically unprepared, when we obtain aliasing or moire, right? So today we want to see how we can get around this moire or the aliasing, such that we can do downsampling like for the color components, prominence, and avoid moire or aliasing. Right. So basically, when we look at the course, we see that it's high spatial frequencies, right? High spatial frequencies cause aliasing when we do downsampling, right? So to avoid it, we simply would have to set those high spatial frequencies to 0 or to reduce them before we do the downsampling. Right? So since the DFT is invertible, the discrete Fourier transform, we can do this in the DFT domain. So in the DFT domain, we have the coefficients which belong to those high frequencies, and we can simply set them to 0. So you can achieve this by setting the corresponding DFT coefficients of these high spatial frequencies to 0, and then use the inverse DFT to produce the resulting image or video again, this time without those high frequencies. Right? So we slightly modify our image or video before we do the downsampling to avoid aliasing. So this setting to 0 can be done with a mask that we use to multiply the 2D DFT with. So basically we have a mask which keeps the low frequencies and sets the high frequency coefficients to 0. So let us assume that 1 is the highest frequency, the Nyquist frequency. So basically we normalize all our spatial frequencies such that 1 is the Nyquist frequency. So the Nyquist frequency, remember, was the highest usable frequency based on the sampling rate that we have. So, and we only want to keep DFT coefficients, for instance, of just 1/4 of this, of the lowest, of the highest frequency. It should be there. Good morning. So basically, this means we want to downsample by a factor of 4 in this example. So before downsampling, we have a Nyquist frequency which depends on the sampling rate that we use in our system, like the number of pixels per degree. And then we want to do a downsampling by a factor of 4, which means our Nyquist frequency is then just 1/4 of it. So that means we have to reduce our frequency content accordingly. We keep just 1/4 of our frequencies, and well, maybe it was right. So we only want to keep the 1/4 lowest frequencies. Right. So in this example, it doesn't have to be 1/4, but in this example we just take 1/4 because it's an easy number. Right. So now we have 640 pixels, for instance. This is our usual VGA resolution that we get from our webcam, for instance. And yeah, that means the DFT has 640 coefficients per row. Right? If we apply the DFT to a complete row of our pixels, then we get 640 DFT coefficients. And because of the symmetry around our center that we saw last time, we just need to consider the lower halves. Right? So we get 2 halves with the same content. This is the first half, and then symmetrically to it, the second half. So therefore, we will have to keep only 1/8 of the total coefficients at each end and set the remaining coefficients to 0. So, it's a typo. coefficients to 0. So a corresponding map for one dimension would be like in this IPython example. So we have our mask, and this is our one-dimensional mask, which we start here in IPython Pilot, and we initialize it with zeros, right, with ones. Then we initialize it actually with ones, and then we set the middle part to 0. And so here you can see that we set the part from 640 divided by 8 to 640 minus 640 to 8 with zeros. So this is basically, except for the 2nth, where we have 1/8 of the total coefficients, everything else in the middle we set to 0, which we can see here in this row. Right. So here the middle part is set to 0, and then we plot it and take a look. And this is the mask for low frequencies. So since this mask indicates which frequencies are passed and which are attenuated, we also call it the transfer function. So we transfer certain frequencies, in this case the low frequencies, right? And we block the high frequencies. So this is how it looks like. So on the x-axis we have the index of the DFT coefficients. On the y-axis we have the value of our mask. And here we can see that at both ends we keep 1/8 of the coefficients, and in the middle we set them to 0. Right. So if we now take this mask and multiply it element-wise with our DFT coefficients, it basically sets this middle part to 0 and keeps the ones on the sides, which correspond to the low frequencies. Right. So, but now we have 2 dimensions, so we need to do the same for the rows. Right. So now we have simply applied the mask for each dimension, but for our mask for the columns, we just need to have slightly different dimension because we have only 480 columns. So this we can see in this Python script as an example. So here we have the mask for the rows, and then we have the corresponding mask for the columns. So C is now the number of columns that we have. So in the VGA example, that would be 480 columns. No, actually the other way around. 480 rows and 640 columns. So each time we keep 1/8 of the low frequencies, and this is then the resulting mask. Right. So here you can see now horizontally, this is the coefficients, the coefficient indices along each row, and vertically are the indices for each column. So vertically you have the row index, horizontally you have the column index, right? So since now each axis is an index for the DFT coefficient, we have to have the third dimension for the magnitude of our mask, and this is represented in color here. So red means 1 in this color display, and blue means 0. So we have a mask, a 2-dimensional mask, where we have the corners with 1s, and remember the corners have the lowest frequencies. So maybe you remember last time's demo where we applied a 2D DFT to a live video, and there we saw in the corners the bright regions, right? Bright little stars in the corners. And these are the regions of the lowest frequencies, and these are the ones that we keep here. Right? And everything is like the stars that we saw when I hold a fine pattern in front of the camera, which appeared more in the middle. This would be suppressed here by this mask. So if we have bright coefficients somewhere in the center, they would be gone after applying this mask. And that's the purpose of it. Yeah, so again, this is our two-dimensional transfer function. And we apply it to the two-dimensional DFT. Right? And from this property that this mask is a filter which only passes the lower frequencies, this is also called a low-pass filter. Right? It passes the low frequencies and stops the high frequencies. So it's a low-pass filter. Yeah, so now we can create a two-dimensional FFT and set the high frequencies to 0, as in this example. So first here, we take this frame from the camera. Here in this case, this would be the green component, which you can see with index 1 in the primary color index. We normalize it to be between 0 and 1, and then we apply the two-dimensional FFT to it, and the capital X now contains the two-dimensional DFT coefficients. And here we apply the mask. So the new X becomes the old X times our two-dimensional mask. So that means that after this step, we only keep the low frequency coefficients. Make sense? So now we remove the high frequency coefficients, and then we can apply the inverse DFT to these new coefficients to get an image or video without these high spatial frequencies. And we do that here by applying the inverse FFT to our low pass filter coefficients. And yeah, remember why I use abs here after the inverse FFT? Why is it here?
Positive real numbers.
Yeah.
Not the we will skip the imaginary.
Exactly, right. Because after applying the inverse FFT, I have complex valued numbers, which is not what we want. So complex valued where we have a vanishing imaginary part. So here in this case I'm using abs because I know that our values should be positive or 0. Or we could also use real, the function real, which only keeps the real part. So in this case, both give me basically the same result. So, but in general, you should use the real function because that also allows negative values. Right? This does not work if you have negative values, but real always works. Yeah, and here I have a little Python script which shows this process. Video FFT 0, IFFT disp. So this takes, the name basically is the program. It takes the video from the webcam, then applies an FFT, then that sets 0, the high frequencies, and then applies the IFFT, and then displays the result. So now I can show you the program here by looking at it using gedit. So copy, Control C, then gedit the name. So here you can see the program. And here you can see in the beginning, again, I'm setting up the video camera. Here I have video camera 0, which is the first video object it finds, which is usually the webcam. Then it extracts the shape, the number of rows and columns by capturing one frame here. And then using the obtained number of rows and columns, here it makes the mask. So we have the rows, the columns, and here is the two-dimensional version. So, do you know what it does with the NP dot? Remember the NP dot, what it does?
Multiply.
Yeah, what kind of multiplying?
Element wise. Element wise.
No.
Row with columns.
Well, it's matrix multiplication. Right? So NP dot in this case is a matrix multiplication because the type of MR and MC is in a numpy array. So in this case, dot is the matrix multiplication. If you just would say MR times MC, then you would have, with a star as a multiplication, you would have element-wise multiplication. With the function dot, you get matrix multiplication. Make sense? So now, what form does MR and MC have? Are they row or column matrices? What is MR?
Row matrix.
MR, let's see, MR NP1s of R, 1. Basically, it means it has R columns and 1 row. Right? So it's a Tor matrix. The first index in ones refers to the number of columns. So that's the index going down. Remember? So the second index of the ones is the index that goes horizontally. So that's the number of columns. And so now we have a vector or a matrix which contains R rows but only 1 column. So that's what you call a column matrix because it only consists of 1 column. It's tall and very narrow. So the MR is the opposite when you look at MC. So MC is ones of 1, C. So it contains only 1 row, but C columns. So this is a wide vector. Wide and very small. So this is called a row vector. So here you have a matrix multiplication of a column vector from the left times a row vector to the right. So what's the size of the resulting matrix?
It just contains a single element.
No. No. So it would be a single element if you would flip them. So if you have a row times a column, then you have first row times first column, you have just 1 element, right? But now we have the opposite ordering. We have
R into C.
Huh?
R into C.
Yeah, right. So we have a matrix of size R times C. It's because when we do the matrix multiplication, column times row, we have first row times first column. And in this case, first row is 1 element, first column of the other one is also not just 1 element, so you just multiply those two as a result. And so on. So you just have, take the corresponding values. So in the beginning you have a 1 for the first, for MR, and you multiply everything with a MC. So basically, first row is MC. And then you repeat MC as long as you have 1s in MR. And then when you have zeros in MR, everything else is 0. And then at the end, you again have 1s in MR and you just repeat MC. Right? Make sense?
Yeah.
And this is how you got this mask where you have the 1s only in the corners. Right? Because you can see it. These are the MCs, which appear unaltered in the beginning, and then everything is 0, and then the MC appears again in the bottom. Right? Make sense? So again, this shows you that getting a feeling for matrix multiplication is important. Particularly those simple special cases where you have, like we saw last time, when you have diagonal matrix, which are really simple, or in this case, you have row and column matrices, which is also really simple. And keeping in mind what that means for matrix multiplication is really helpful. And it also allows you tricks like this. So remember, this here is basically replacing a for loop. And in Python, a for loop is really slow. So if I could do this with 2 nested for loops to create this mask, then it's quite slow. I mean, here in this case, it's just for setting up the mask, so it wouldn't really matter, but if you would have this executed for each frame, then it would be a problem. Right? So matrix multiplication allows you to replace for loops, in this case even nested for loops, and then it gives you a lot of speed gain. And that's important for video processing because you have a lot of data which need to be processed in high speed. Right? Makes sense? So it's basically a trick to speed up this program. Yeah, so once you have the mask, you can then go into this video processing loop, this infinite loop, which continuously reads frames from the camera here in the beginning with cap read. And then it shows it. So imshow, it just displays the just obtained frame, but only the green component here. So this is basically a simple way of displaying a black and white image, right, without doing the conversion to Y. So then I apply the FFT, the 2-dimensional FFT, to this green channel. Apply the mask. Then here I'm making a frame for display. Here I show the frame. So this is basically containing now the DFT coefficients which remain after applying our filter mask. Then I apply the inverse FFT. So here observe that there's no apps here, right? I only applied the apps for displaying purposes because X contains complex value numbers and they are difficult to display. Right? But the magnitude is much easier to display, and the magnitude is actually what's interesting us because we want to get rid of the high frequency components, and that will show up in the magnitude if everything is black. So here I'm doing the inverse FFT and then apply the apps here to obtain real values, and then I show it here in this next imshow window. And I do this until I hit the key Q, then it ends my little program. Make sense? So basically applying FFT, multiply the mask, apply inverse FFT and display. So now we can try it. So make that a little larger here. So now I execute it using Python 3. Okay, so now you see the corresponding 3 windows. Remember, we used 3 times imshow. So here on the left you see the original. This is the green component, basically a cheap version of a black and white version of the video here. This is the DFT, the 2-dimensional DFT, after applying the filter mask, the low pass filter mask. And you see indeed only those low frequencies are left. And if I'm applying again my fine pattern here, you will see that it doesn't show up anymore. Let's see, where do I have it? Here you go. So here I have my fine pattern. So this still shows up. Right here you can see it. But when I go further away, then you see it would go to the middle, but it's not, because now I applied my low pass filter. And you can also see in the reconstructed image the effect. So when I'm closer, you see the reconstructed is still identical, but when I go further away, now it's still there. So now the bright dot disappears and also the pattern in it, right? Can you see it? So now it's just gray instead of those stripes. And you can see it here in the frequency domain. In the frequency domain it disappears. And that means also in the reconstructed domain it disappears. All what's left is a gray colored area. No fine pattern anymore. So this is the effect that you get from low-pass filtering. You basically remove those fine patterns. And remember, this is actually what we wanted, right? We wanted those fine patterns to disappear because they created trouble, the more array, in the downsampling process. So, Q. Yeah, did you also see another artifact here? It's kind of interesting. When you just look at the result here, this picture, what do you think? How does it look like? Do you see those stripes here?
Yeah.
So these are artifacts from low-pass filtering, and they are called ringing artifacts. Because if this would be a tone audio, then it would sound like ringing, like if you hit a bell or something, right? So here, hitting of a bell is equivalent to this edge, right? A sudden change in brightness, and that results in those ringing, those up and down, near the edges. Right? So this is the typical filtering artifact that can appear, and this also shows a problem using low-pass filtering. You actually have to be careful in designing this low-pass filter to avoid those artifacts. Right? Because our goal was to avoid artifacts, array artifacts, but not to create new ones. Right now we have created new artifacts in this way. Okay. So back to the slides. So here we saw, in fact, it has less high spatial frequencies and hence looks more blurred. Yeah, so we know from signals and systems, hopefully, that a multiplication in the Fourier domain corresponds to a so-called convolution of the corresponding signals in the spatial or time domain. Does everybody know what convolution is? Faltung? Yeah, everybody knows? So you should think about signals and systems. This is basically one of the first concepts that's taught in signals and systems. So basically here we have the same, right? We have a multiplication in the frequency domain, and this multiplication in the frequency domain, here in this DFT domain, is convolution in the time domain or spatial domain. So we can convolve two pictures, and that's the same as multiplying the corresponding Fourier domains. Make sense? Have you heard about this equivalence between multiplication in frequency and convolution in time? Okay. Yeah, so here it's not exactly convolution, but circular convolution, because we only have finite length signals, and hence only a finite length Fourier transform. So we have the DFT, the Discrete Fourier Transform, which is based on finite length signals. And that's why we have those periodic frequency domains. Right? Remember, this frequency domain repeats after 2 pi, basically, or at the end of the DFT, it would repeat. And that's basically why when we do a convolution, say we do a multiplication in time, we would have a convolution in frequency, and then we would see directly that it's a circular convolution because of the repetition of the spectrum. The same is true for the inverse DFT. When we have the inverse DFT, we get a signal piece, but we have to think about the signal piece as one period. It would actually continue. And if you do multiplication in the frequency domain, you would have a convolution with this periodic continued signal in time or space. Yeah, so this is how you would write it as a formula. Here is the convolution, And here I have this capital N here next to this convolution star, which means we just have this circular convolution. Here it appears as the modulus function for the index of this second time domain signal h, or second space domain signal h. Do you know the modulus function? So if you have, for instance, something modulus 4, then you have 0, 1, 2, 3, and then begins again. So 4 modulus 4 means 0, 5 modulus 4 means 1, and so on. Right? So you begin at 0 again. And this is basically the effect of this circular convolution. It continues to convolve, but it begins again and again for this second time or space domain signal. Yeah, so basically this convolution sum runs in a circle. Yeah, and in our case, this h of n is the inverse FFT of our mask M, right? So the second entry. So instead of multiplying our mask in the frequency domain, we can also convolve it in the space domain with our image. So this was actually would save us the FFT. Right? Instead of going to the Fourier domain and back, we just convolve directly in the space domain to have our filtering effect. And this can be seen here. So we have our mask again. The mask for the rows. So each row has this length of 640. So same thing. And here you apply the inverse FFT to it and plot it. And here you can see the result. So this is the result of the inverse FFT of each row of our mask. Right, or of our row mask. Does this remind you of some function that you know? Very interesting. I mean, it's just like this decaying ring at the beginning, and then the same mirrored from the right hand side.
Impulse.
Yeah, what do you mean? Does it remind you of the sinc function? It looks a little bit like a circularly shifted sinc function. Right? If this pulse here would be in the middle, then it would look like a sinc function, which we already saw as the when we looked at the receptive fields, right, of the eye in the retina. So, and since we do a circular convolution anyway, we can shift it circularly. Right? It doesn't really matter. And if you do this, we get this. So here we shift it by basically half the frame size, half the number of rows, cyclically. So basically we just switch the two halves. Right? The right comes to the left and the left goes to the right. And then we get this result here. You see that it now looks more like a sinc function? So here you can see the middle part, this is the main lobe of the sinc, and then we have those ripples to both sides, which basically continue to infinity in theory, and slowly decays. And this is actually also what you would expect, because the FFT of a rectangular function, which basically our mask is a sinc function. Right? Our mask, remember, was two rectangular functions at the end. We can also apply the circular shift there. Then we have one broad rectangle in the middle. We apply the inverse FFT, and then we get a sinc function. Right? The sinc is the result of a rectangle. The FFT, the Fourier transform of a rectangle. Make sense? So this is actually what we see here. So, yeah, because of this circular nature, it's not exactly a sinc, but similar to the sinc or SI function. Yeah, and this is similar to the receptive fields in the retina. Yeah, so now after low-pass filtering with this sinc function, we do downsampling. Now we are allowed to do downsampling by a factor of n, and this means we take only every nth pixel of the resulting image, or every nth sample. And this corresponds to the substitution of our index lowercase n in the convolution equation by m capital N, where m is an integer. So now here, instead of lowercase n, we have m capital N minus I. So again, this circular convolution. Makes sense? So this is now circular convolution using downsampling. So here you can see we just take every capital Nth sample and ignore the values in between. So this is now a downsampling. For instance, for the color components, where capital N could be 2 or 4. Yeah, so this sum shows us we compute, for each sample ym, we compute the sum over the shifted impulse response of the filter at position mn. Right, so here we have this filter located at this position, shifted to this position, and then we compute the sum of the product of the two signals h and x. And basically we are shifting the sum over the signal. And we are not continuously shifting, but we jump by n samples. So you can think of, you have the signal, and then you have this impulse response, and you shift this impulse response by n samples, capital N samples, over the signal. So for instance, take our already calculated impulse response, hc, which we just saw, and set capital N equals 8 just for this example. And for two adjacent positions, m and m plus 1, we get for a section of approximately 40 values this plot here. So here I have a plot hc from 300 to 340, and here hc 308 to 348. So here it's already shifted by 8 pixels. So this is then the result. Right, so here you can see the two shifted versions, kind of close to the center. Right, here you can see how they jump by 8 samples. So now you can imagine that underlying you have your pixels from your image, and then you take those pixels and multiply them with each of those functions. And multiplying with the green one and summing up gives you one low pass and downsampled pixel. Doing the same with the blue one gives you the next pixel, and so on. So for each new pixel we have to do this multiplication and summation. Right? And this actually shows you that it's a lot of work. Right? So each new pixel requires, well, at least those 40 samples. Right? So for each new pixels you have to do 40 multiplications and summations. Right? So the green results in a new pixel, the blue curve in another one, and then there will be more. So each new pixel requires, in this case, at least those 40 multiplications and summations. Yeah, what do you think? Does that work? Maybe, if your computer is fast enough. Yeah, so here we also see an overlapping of the neighboring impulse responses. So they're shifted, but there's a lot of overlap. Right? And this is actually the reason why we have nice smoothing of our image. Yeah, so this also corresponds to the overlap of the receptive fields in the retina. Remember this picture from last time? We had those circles for the receptive fields, and those different circles were overlapping. So that means that each light receptive sensor in the retina was connected to several nerve fibers going to the brain with different weights, right, from this overlapping receptive fields. And this is basically also the case here. Right? When you look at those, there's a lot of overlap. And each sample here in this picture goes to the output of neighboring pixels. Say, for instance, pixel number 15. So if you imagine those pixels are below here, pixel number 15 goes to the output of the green pixel, and it also goes to the output of the blue pixel, which comes next. Right. So these are the overlapping receptive fields. Here in this case, the overlapping impulse responses. Yeah. Does it make sense? So we have the same pixel of the input image goes to the result of several image pixels at the output image after low-pass filtering and downsampling. And this is actually important for the smoothing effect. Right? We don't want to have the next pixel jumping a lot at the output, because we want to smooth it using this low-pass filtering process. Yeah, so now we can also try it again in this 2D mask, two-dimensional mask. So if we now, instead of just using one dimension as we just did, apply it to our two-dimensional mask, basically we get a comparable result. Now just we have to use color displays. So here the same mask as before. So here we have M. M is our two-dimensional mask. Here we have now the inverse FFT of our mask. So now this lowercase h is our mask in the space domain, and since it's the inverse DFT, we also call it the impulse response. Right. And again, we rotate it like we did before. Here we rotate horizontally, and here we rotate vertically, as we did before. Now it's just two-dimensional, and now we show it in the center part using false color display. So here we actually used ImShow, and ImShow uses for images which are not color but have only two dimensions, it's not a three-dimensional tensor, then ImShow automatically creates false colors to more clearly see slight differences in magnitude. Right. So each magnitude has a different color, so that you can easily see slight differences. So this is then the result. So here in the center, we have high values. So horizontal axis is now pixels in the space domain. So 20 pixels times 20 pixels. Then in the center, you have the largest values. So this is the main lobe of the sinc function. And then when you go off the center, you get smaller values. And you also get negative values like the violet parts here. So we have those ripples, but now in the two-dimensional case. So basically you have the same sinc, but now not just along x-axis, but also along y-axis. Make sense? So since the two axes now are used for space indices, the third axis, the magnitude, is the color that we can see here in this picture. Right. And now when you look at this shape here, it actually has some resemblance to the receptive fields in the retina. It's not exactly round in this case, but it's somewhat round. Right. So it's not exactly the same, but similar. So it resembles the receptive field with this lateral inhibition. So this shows you that basically this low-pass filtering and downsampling that we just saw is basically the same principle that happens in the eye on the retina. Right? The retina is basically doing the same thing. It's doing first low-pass filtering and then downsampling to avoid moray. Because for our brain it's also important not to see patterns which are not really there. Right? We don't want to hallucinate. We want to see what's really there. It's important for survival, at least in early times, I guess. Yeah, and a good visualization of this two-dimensional convolution with a two-dimensional impulse response, the receptive field, followed by downsampling, can also be seen in this little video. So this is a motion PNG. And here you can see the blue block here is an image. This gray block would be our impulse response, our low-pass filter. And then the green one is the resulting new image after low-pass filtering and downsampling. Right? So you can see here the gray block jumps over the image in steps of 2. Right? So here we would have a downsampling factor of 2 along the rows and the columns. Right? So for each new pixel, we take the pixels of the original image and multiply them with the values in this gray filter impulse response. Right? We take all pixels, basically we have a weighted average with the weights of those filter impulse response, sum them up, and that's the result of this new green picture. So here when you see when it appears at the first pixel 1, then basically it looks at this weighted average at the first position in the upper left hand corner. Can you see it? So I think this is actually quite a nice visualization of what happens when you do filtering and downsampling. Isn't this nice? So maybe this helps to imagine what happens in this two-dimensional convolution including downsampling. Basically you shift this filter impulse response over the image. At each position you get a new output pixel value. Right? And since you jump by a certain number of pixels, you have the downsampling as part of it. Yeah, and actually this example is from a deep learning website. So here you can now see the connection to deep learning, because in deep learning we have the same problem, right? We have some image that we want to recognize, and in deep learning basically systems do something quite similar that our eye and brain is doing, because the task is basically the same. Our brain wants to recognize something, and in deep learning you often also want to recognize something or classify something. So it makes sense if our system is optimized for this task, that machine learning should come up with the same optimal solution. Right? And that's why basically you see this same result. Yeah, so actually this is quite a nice tutorial about convolutional neural network, which are also using 2D convolution with downsampling. Have you heard about convolutional neural networks? Have you heard about machine learning?
Yes.
Yeah, so machine learning is using convolutional neural networks, particularly when it's about recognizing objects and images, or for instance also speech recognition. Right? So what you see in recognition tasks or classification tasks is most often convolutional neural networks. Yeah, and they have slightly different terminology. So they call the downsampling strides. So in deep learning you see strides instead of downsampling factor, but it's basically the same. Yeah, so this animation does not work in PDF, so you can go to this website to make it animated. Right. So here's a little Python example from the library SciPySignal. And it already contains a function for 2D convolution, SciPySignal convolve 2D, and it assumes that x and h are two-dimensional arrays, right? Type array, 2D array. So x could be our frame from our camera. So that would be, for instance, black and white frame or the green component, and h is the low pass impulse response. So now we can use this script video fit disk. So actually this uses convolution in the space domain instead of the FFT. Right? And then it displays the result. So here we calculate the impulse response h as an inverse FFT of our transfer function m. And we must limit the size of the 2D impulse response drastically so that a real-time processing is possible. So this is the problem that I was mentioning before, right? Like those 40 pixels that we saw. Turns out actually 40 values for each new pixel is too much to compute in real time. So we have to limit it more. So for FFT filters with large impulse response, the calculation using FFT is much more efficient than the convolution. Right. So it turns out, after all, that going to the FFT domain first, applying the mask there, and then going back is actually much faster than doing the convolution directly. So let's now take a look at this file here, video filled disk. Copy, Control C, gedit, Control Shift V. So now we see the resulting program. So the beginning is the same as in our first example. Here we compute the mask for the rows, for the columns, and here the 2D mask as this matrix product. And now here, this is new. Right here in this part, line 23 and following, we compute the inverse FFT from our mask. So here, inverse to the FFT, and then we do the rotation. Here, left and right is flipped, top and bottom is flipped to get what we just saw. And this is our filter. So filter is our HC. And here's our video loop, the infinite frame, which is actually now quite short because we don't have to go to and from the DFT domain. So here I'm actually computing the Y component. So instead of simply taking the green component, I'm just computing the Y component for a change. So this is the actual more precise black and white image. And then I'm applying my 2D convolution, convolve 2D, on this black and white image Y, convolving with the two-dimensional filter impulse response of our low pass, and mode equals same. Do you know what mode equals same means? Have you heard about it? So when you look at the example that we just saw, when you do the convolution, how big is the result without downsampling? So avoid downsampling for a moment. How big is the result? Well, this is actually the problem that is tackled here by mode. Usually when you do the convolution, you zero pad finite length signals. So like in this example that we just saw here, we basically zero pad the original. So here you can see there are zeros around it, and then you shift the kernel over it. Right. And if you do it all the way to the up to the case where until there's no overlap between the two versions, then the result is bigger than the original because of this overlap at the boundaries. Right. So after convolution, the result with the zero padding would increase. But we don't want that. We want to have the output the same size as the original. And that's why we use mode equals same. And that means that convolve 2D, just zero pads enough to obtain the same size. That the output of convolution has the same size as the input frame. Makes sense? So this is basically convenience, so that we don't create different sizes. So basically similar to data size, data types. Here we just make sure that the output array is the same size as the input array. So, no, that's not it. I just want to type this. Yeah. So here mode same means it's the same size as y. So that's just convenient for us. Alternatives is valid, which gives everything until the overlap is zero, until there's no overlap between the two, or valid with valid, and the other one was full. Full gives everything, and valid gives only the result with no zero padding. Right? And then the output is actually smaller than the input, which is also something we don't want. Yeah, so this is convenient that we have the choice here, and then yfit contains the convolved version without downsampling. Right, so here we save the downsampling step. So that's one of the reasons why it's more complex, because the output image is the same size as the image. So now we can run it. So here we display the low-pass filtered version with a suitable attenuation factor to avoid overload from filtering. So now we can run it. Python 3. Oh, by the way, they stopped supporting Python 2 starting next year. So it's worthwhile to switch to Python 3 because Python 2 is running out of its lifetime. So here you can see it. Yeah. Can you see that it's low pass filtered? It's kind of unsharp. And can you also see the low frame rate? It's like, I don't know, maybe 2-3 frames per second. And I have actually quite a fast laptop. If you have a slower laptop, it's even worse. So here I'm trying my stripes again. So when you're close, the stripes are still there, right? So when I go further away, yeah, about now it's just gray, right? No pattern anymore. So the same effect as before, using the FFT, but you can see it's much slower. But look at the ringing artifacts. What about the ringing artifacts? Do you still see ringing artifacts?
No, they don't.
Yeah.
Most of them make there's something, but
Yeah.
I suppose it has to do with we cut away the high frequency parts of the filter, so maybe it has to do with that.
Yeah, actually we didn't cut the high frequency parts, but the ripples in the space domain. Right? So you're right, so that's actually the reason. And when we look at the program here, we can see that here we only take plus minus 10 coefficients. Right? Here you can see r over 2 minus 10, r over 2 plus 10. So that's basically the center of our sinc function, plus minus 10. So it's quite a lot of cutting, right? When you imagine that the original impulse response was 640 by 480, and what you keep is actually a small 10 by 10 center. So most of the ripples we actually threw away. And that's why we basically have almost no ringing left, because I cut those ripples which are responsible for this ringing away. And that's also why we get a different result. Cutting off those ends means we now do something similar, something different, similar but different from what we did before. Right? We still do low-pass filtering, but a different low-pass filtering. Yeah, but also it's kind of disappointing that it's so slow. Yeah, so this actually shows that it's worthwhile to go to the DFT domain. So it looks quite similar to the implementation using the FFT, except for less ringing artifacts. Right. Yeah, so thus we see that the receptive field on the retina correspond to a filtering of the image, and the distance between the nerves correspond to the downsampling for the smaller number of optic nerves. Right. And we can actually also take a look at the resulting transfer function of the human eye, or we can probe it. It's actually measured experimentally by visual test. And this results in the so-called contrast sensitivity function, or short CSF. Right? So we saw basically eye is doing filtering and downsampling, so that means we can also measure this filter. So this is how it looks like. So here we have the spatial frequencies in periods per degree. So now this is not the index of our DFT, right? Because this has to refer to the eye, measurements of the eye. And this hence needs to be periods per degree, because that is what the eye is seeing. Right? If you look at some image, then you have a certain number of periods per degree of measured from your eye. Right? So you have 1 degree, then you have a certain number of stripes that you can see. And when you make those stripes finer and finer, more and more in this 1 degree, then at some point it's just gray and you can distinguish them anymore. Same as in my test image. Right? We looked at the test image with the stripes, and then I went away. We have more and more stripes per visual angle from the camera, and at some point the stripes turn into gray. And the same effect happens to the eye. So if you have a stripe pattern and you hold it in a person's face or in front of the eyes and you go away, then you have finer and finer stripe patterns, and at some point it turns into gray. And that's the limit of your vision. And also, it turns out it makes a difference how bright and dark those stripes are. If the stripes are more or less gray between the brightest and the darkest part, then it's more difficult to distinguish them, and then it turns into gray earlier than if you have dark black and bright white of your stripes. So that corresponds taking this pattern here and shining with differently bright light on it. So if you have bright light, I can go further away and you still see the stripes. But if I have very dim light, say at moonlight, it turns earlier into just gray. Right? And this is called contrast. Right? If you have larger contrast between black and white, if the difference is larger, then you have higher contrast. And this is also what you can see on the other axis of this image. Vertically is decreasing contrast. So on the lower end here you have the highest contrast, and at the upper end you have the lowest contrast. And then the lines show you where the boundary is between seeing stripes and just seeing gray. Right? So here, those lines are the boundary to seen gray instead of the stripes. Yeah, and here you can also see the influence of the light. If you have bright light, then the maximum of the sensitivity of the eye is at the higher spatial frequency. So here you are at about 2 periods per degree is the maximum when you have bright light. And if you have dark light, it's about 0.7 periods per degree. And it's the peak because at that point the eye needs the lowest contrast to see the stripes. Right? So even at relatively low contrast on the paper, for instance, you can see the contrast when it's in these numbers of periods per degree. So basically you can also say, instead of periods per degree, you can say stripes per degree. Right? So many stripes per degree. One stripe, bright, dark is 1 degree. It's 1 period. Makes sense? And this is actually quite similar to how cameras are measured. So for cameras, you actually do the same trick. You use those stripe patterns here and take pictures of those stripe patterns. And for different cameras, you can actually see how finely they can resolve fine patterns. Right? So you make those patterns finer and finer, and you can then tell at what point the camera can just see gray instead of a fine pattern. So in cameras it's called modulation transfer function. Here for humans it's called contrast sensitivity function. But it's a similar thing. Yeah, and I guess this curve could also be used for advertising because it tells you what patterns are easily visible. So if you have a pattern in an image which falls into the maximum here, like here those 2 periods or 0.7 periods in this range here, this is actually what catches the attention of the eye. Right? It's basically passed with the highest intensity to the brain. Yeah, so we can also see now that it's basically not exactly a low-pass filter, but a kind of a low-pass with an increase at the center frequencies. Right? So you can see the high frequencies are attenuated effectively here in this region, but then also the middle frequency, they are increased. Right? So we have this increase in the middle frequencies, and this is basically the effect that edges on objects are amplified for our brain to make object recognition easier. Right. Yeah, so our eye is most sensitive to these center spatial frequencies. Yeah, and through adapted tests, the CSF can also be measured or determined from eyes of other living creatures, which is kind of interesting. So biologists did tests on several animals, for instance goldfish. They were even able to determine the contrast sensitivity function of goldfish. It's kind of amazing. So here you can see the maximum for goldfish is actually much lower than for humans or macaques. Macaques are actually kind of monkeys, right? So in a way very similar to humans, which you can also see here in the contrast sensitivity function. It's not so different. Goldfish they don't have that sharp vision, right? So that's why the maximum is at much lower frequencies. And also cats, right? Cats have a contrast sensitivity function maximum at much lower frequencies than humans. So you could also argue that cats have less sharp vision, which I guess also makes sense because they mostly hunt at night, and at night you don't see that many details, I guess. Here's the barn owl, the pigeon, they are coming closer to the maximum of the human, but they are actually not as sensitive, maybe because they are mostly hunting at daylight. Here the eagle and the kestrel, I'm not sure what the kestrel is, but the eagle is flying high, and he needs to have telescopic eyes basically to see his prey on the ground. And that's why his maximum of the contrast sensitivity function here is at clearly higher frequencies than for the humans. So the eagle is able to see much finer detail than humans. Yeah, so again, everything on the horizontal axis is cycles per degree. So, or you could also say strikes per degree. So you have an angle of 1 degree, and then you can count the number of strikes or periods, and that's your spatial frequency. Make sense? So basically this is how fine your pattern is. And vertically you have the contrast sensitivity. And sensitivity means 1 over the contrast that is needed to see something. So when you have a high contrast, that means 1 over the contrast is low. That means your eye is not very sensitive. So then you're at the low end here, for instance 1. If you have a low contrast that you need to see something, then 1 over the low contrast is the high number. For instance, 1 over 0.1. If 0.1 is the contrast, then you land at 10, right? And that means you're more sensitive. So this sensitivity means basically 1 over the contrast. So a higher number means lower contrast is necessary to see the pattern. Make sense? Yeah, and here you can also see 2 different contrast sensitivity functions for the human eye. 1 for color and 1 for sensitivity, for intensity. So, and it makes sense that you have a difference there because remember, the light sensitive sensors for color are much fewer than the light sensitive sensors for intensity. Right? You have the cones, you only have about 6 million light sensitive cones for the color, and then you have the rods for intensity, for luminance, right? The black and white vision. You have about 110 million of those. So it's a big difference. And when you think about those numbers and then compute the density on an area, so the retina is a surface, 2-dimensional, so then the density would be the square root of those numbers, right? Because the total number is horizontal number times vertical number. Make sense? So the total number is basically the square of the density. And that means when you take the square root of 100 divided by square root of 6, the million cancel, then you come to roughly a factor of 4. Right? So the density along 1 dimension is roughly a factor of 4 between the rods and the cones. And this is also what you roughly observe here. So here you have a maximum roughly at 4 periods per degree, and for the cones, the color, you have about, I don't know, a little bit less than 1. So it's actually a little bit more than a factor of 4. Right? Make sense? So this shows you that the eye for color and for intensity has different contrast sensitivity functions. And this is actually something that is used in video coding. Right? There's different sensitivity for color and brightness. Right? Yeah, so this is actually an important property here that we can use for compression. Yeah, so after downsampling, we still need to reconstruct the image in the decoder, right? Or in the receiver. So we can now transmit a downsampled image with a downsampled color components, for instance, without the zeros between the samples to the decoder, and hence with fewer pixels and thus a smaller bit rate. Right? Fewer samples means reduced bit rate. But how do we reconstruct a picture with the original size? Right? So now we transmitted a smaller picture, but in the decoder we have to still enlarge it to make it original size. So we have seen that if we just put the transmitted pixels in the right place, leaving the other pixels at zero value, we get a picture which consists of many small points. So that's not good. Right? It is interesting to look at the spectrum of this point image. And this is done with the following Python script. So we can do the downsampling as usual, keeping the zeros in place. Here this is the DS, the downsampled version. Y0 is the original, and we only keep every end sample. So we go from 0 to the end in steps of capital N. Right. So then this DS actually it has no zeros, right? Because this only consists of the non-zero entries. So DS has much fewer samples and then is transmitted. On the decoding side, we need to upsample by reinserting zeros to obtain the original image size back. So this is down here. Here we have the upsampling. So DS0 is initialized with zeros in the original image size, and then every nth entry here gets assigned the value of DS. Right? So in this way we have the original image size, and every nth sample horizontally and vertically gets a non-zero value. So then we can actually take a look at it using this program video FFT0 IFFT resample key. So it means we take the video, apply the FFT, setting 0 the high frequencies, then apply the inverse FFT, and then we resample the Y component, and we have a key control. Right? So here we can actually turn on and off sampling and filtering. So we can turn sampling on with key S, and there we will see the FFT, the 2D FFT of the sampling on version contains periodic repetitions of the spectrum in the X and Y direction. Right? So it repeats the spectrum. Since these were not present in the original, they represent artifacts, namely our aliasing. The corresponding decoded video corresponding consists only of those small dots. Right? So that shows if we have this dot image, then the spectrum has those periodic continuations or periodic copies. So to avoid or reduce the aliasing, we could simply set the periodic spectral copies to 0. And this works again with our mask for the low pass filter M, which we apply again in the FFT domain. This should be called domain. Yeah, this time in the decoder. Right. So the reconstructed image in the decoder in the window decoder filtered sample frames actually looks almost like our encoder in the low pass filtered image, and that was actually the purpose. Right? We are able to reconstruct the low pass filtered versions. So let me take a look at it. Copy. So now I open it with gedit. So here you go. So it starts as before. Here we have the initialization with zeros of the original frame size, DS0 and DS. Then we compute the mask here, as before, same thing. Here I'm now creating a text for our image as kind of a manual to show how it's used. Here I have two flags. Filter on is false, which tells the system if we turn on the low-pass filter, and here sampling on, which tells the system if the sampling is on or not. So here we compute then the Y component. Here we create the original together with the text. Right? So this is kind of an easy way to include text in our display. And then here are the processing steps which depend on the flag. So if the filter is on, then we apply the FFT, the mask, and the inverse FFT. If the sampling is on, we do the downsampling. So basically this is keeping the zeros in place. So this is the encoding side. Then for the decoding side, so again we have the text here, sampling on. If sampling is on, else we display sampling off. So that's easy for checking the state. Then here we apply the inverse FFT of what comes from the encoder. And if filter is turned on, we apply the mask here in the DFT domain. And if sampling is on, then we scale it to get the original energy back, because from downsampling we lose most of the samples, and that means we lose most energy, and that means the resulting image would look much darker, and this is what we avoid here with the scaling. So then we show it here. And finally we apply the inverse DFT to show the result in the original space domain. Make sense? So here I am now able to switch, and here you can actually see with the wait key I am now checking which key is pressed. So key contains the most recent key press, and here it just compares which key I pressed. If S, I toggle sampling on or off, which I do with sampling, is sampling on equals not sampling on, so it's toggling between false and true. Do you know what toggling means? So if it's false, it becomes true. If it's true, it becomes false. Right? Same for filter. And then depending on those flags, it controls the processing here. So this is an easy way to turn on and off processing. So now let's execute it. Oh, what did it do? Jeez. There we go. Python 3. Yeah, so that works. So again, we have those three windows. So here you can see the text, which is kind of a manual. So now it's the original. Here's the frequency domain, and here's the reconstructed. So the reconstructed is identical because basically I'm doing nothing in between. So here I have again my test image, and you can see here when you look in the frequency domain, you have those high frequency dots which appear in the frequency domain. Right. So next step, I can hit key S for sampling. So now I'm doing the sampling, and you see here we get this periodic continuations or copies. So basically this and this is copied in between and also vertically. Right. So here we can see we get 3 copies, or altogether 1, 2, 3, 4, 4 versions of our components. Right. So this happens when we do sampling. We get multiple copies of the original spectrum. And this is how it looks like when we reconstruct it, using the spectrum with the multiple copies. Right. We get dots. Now the reconstructed image only consists of dots. And you can see we get the alias effects, the moire. Right. Can you see the moire in the reconstructed image? So it's clearly visible, I guess, right? So this is not good. So the reconstructed does not look good because we just take the pixels as they come and fill them up with zeros. So now I can turn the filter on, F. So now we are applying the mask in the frequency domain, in the DFT domain, and you can see it's looking much better, right? So now I'm also trying this pattern here, and you can see the pattern is actually just gray, as expected. So when I'm getting closer, you can see the pattern here, but when I'm getting further away, now it's getting gray. And you can see it also here in the frequency domain. When I'm closer, here you can see the high frequencies are still there in the frequency domain. But when I'm getting further away, so now they disappear because now the low-pass filter prevents those high frequencies. And then the resulting pattern turns into gray in the reconstructed version. So here it's still there, high frequency and reconstructed, you can see it. And now it's disappeared in the frequency domain, and it also disappeared in the reconstructed space domain. It's just gray. Right. So looks much better, right? Using this low-pass filter. We avoided this point-like representation, and we avoided the aliasing or moire. So that's why this is how it's done in video coding. Right. Yeah, so in summary, we have our encoder-decoder sequence containing the following steps. In the encoder, you have first low-pass filtering, then downsampling, then removing the zeros. In the decoder, first you have filling in the zeros and then the low-pass filtering. So reverse steps. So in this way we are able to reduce the number of pixels to be transmitted by the factor of n times n. So that's our compression ratio. With the same image size, but at the expense of some image quality. So this represents a further compression opportunity or capability. And the problem is now to choose the number of transmitted pixels or the resolution so that the eye does not perceive the blurriness. Right? We don't really like this blurriness. Yeah, so in the end I have some references and then a little bit about quantization, which I guess I can do next time. Okay, questions at this point? Okay, I guess then we are done for today. So thanks for your attention and have a nice day.